work in the case of 2D and 3D, image queries, and finish off with some conclusions. So the typical example in the patient handling is, somebody develops some symptoms and he is administered his admission, and then somebody evaluates these symptoms, and based on that we build a hypothesis, and it is based on that hypothesis that we decide the nature of the tests that need to be followed, and these might include blood tests, physicals, microbiological tests, and the kind. And based on these measurements, essentially the results of the tests, we decide if further investigation is needed, and sometimes it is imaging that is being kicked in as the next step. And usually, with the imaging into the loop, then we can decide if this hypothesis is confirmed or annulled, or if we need to revisit the problem from the beginning. So the problem statement is as follows. So we have the initial set of testing that pretty much can be analyzed with, it's tabular data, numerical data, so it can be analyzed with conventional data science workflows, and we can utilize everything up to artificial neural networks, representing probably the state of the art out there, and draw some conclusions from this analysis. On the completely different domain of medical images, we can use convolutional neural networks, which is a very well-established approach, and we can draw our conclusions based on that. But one thing that we do notice is that the two technologies do not intersect. So you've got numerical data handled in a separate way, in a separate manner from the optical data. So the question is, can we bring them together? And why do we want to do that? Because simply because we do see that medical images offer valuable insights that indeed can confirm or reject the initial hypothesis. And these insights can be identified, enumerated, and complement the original data. So, we've got everything that we start with, which is the lab tests. And the question is, can we actually do a better data science if on top of that we were to add numbers that represent the conditions that are visualized? So pretty much the challenge becomes translate evidence into numbers. And by doing this, we are aiming at enriching our original data sets. We enable for better predictions. We discover new unseen patterns simply because now we can combine optical and numerical data, and further introduce automation to greater extents. So how we do that? We actually build a query mechanism for accessing the image information content. So you can think of it something like the SQL language, but only this time around we do not look for numbers or numerical patterns, but instead we're looking at features in the images that are of interest to us. So this type of mechanism allows us to pose questions into the system of the kind like, how does a tumor, for example, look like in this organ, and where is it with respect to everything else? And in order to be able to work with such queries, we deployed a very advanced graph technology framework that encodes the image information content and gives us easy access to it. So at the end of the day, what we're aiming at is to present a suite of tools that includes a processor that extracts any requested evidence, that is pretty much segmentation with custom criteria, a processor that measures all distinguishable features, and I'm making this remark because you might actually extract hundreds of features out of images. The question is which ones are relevant to the condition you're trying to analyze. And we have a processor that builds a statistical representation of the acquired features because we want that extraction to contribute towards some kind of a knowledge base that we will deploy in the future for further processing. And eventually we have a processor that delivers this knowledge on unseen data for instant segmentation and beyond. It might sound a little bit complicated, but as we go along, each one of these will become more clear. So looking at the machine learning approach and artificial neural networks in particular, what we have in the first part of this game, let's say, with the tabulated numerical data, is that we have measurable indices or signals that are the training data, the independent variables, and then we have the results of the visual inspection, if imaging is to come into play, that are the labels. So you've got some numbers telling that there is a potentiality for a tumor, for example, or a cancer, and then the doctor will do all he needs to do, and then see the results, the optical evidence, the optical data, and will actually give you the label. It says yes, indeed, these numbers correspond to this condition. So we can build a model that establishes the relation between the two, that is to identify or propose conditions automatically. How do we throw images into this game? So we want to involve the images into the data science loop. So ideally, we'd like to extract image contents coinciding with the targets according to the expert opinions. That is, like if there's a tumor, for example, in the organ, we want to be able to have a mechanism that can fine-tune our query to the specific area that coincides with that tumor in the image. We want to have the ability to profile the extracted objects. That means, to calculate all the features, the numerical features that describe it best, if it's size, shape, you name it. To concatenate the new feature sets with the old ones, and to pursue a prediction quality improvement through feature selection and model building. So, as you actually extract more and more features out of these images, you want to put them pretty much back with the original data you had and see, if you train a network using the combination of all those, whether that gives you an ability to improve performance in your workflow or not. This is the EDA. And eventually, once we identify the relevant features, retrain the model and deploy it at scale. So this introduces the following challenges. That is to organize the image information content, to attribute all identified clusters of pixels that coincide with our targets, to enable iterative queries, to produce segmentation as query outputs, and this is something that we address with the technology referred to as the grapher. Then we have the exploratory data analysis, which pretty much involves the next two lines. That is to structure a multidimensional feature space, to project segments into that feature space, and to identify the most prominent and discriminative features in the feature space. And once we're done with this, we proceed with segmentation, which is pretty much the process of producing segments on previously unseen images, and these can be used in a number of different ways. So the features that we measure are in the order of approximately 120 different distinct features, and they can be extracted out of 2D or 3D data sets. And we have, to be a little bit more precise, we have a very rich set of class of shape descriptors. We have size, texture, density, homogeneity of components, intensity, relative location, and proximity to various landmarks, organs, and anatomical features on the body. Regarding the tools that we use, I mentioned before the grapher, and the grapher is pretty much an autonomous system deciding on the best data structure. It's a graph data structure algorithm that is going to be used to encode the specific class of images that we are feeding it in. And once this is in place, then we have the grapher in itself allows us to run a number of different query operators. These are image data mining operators that are implemented directly in the graph. And what you do is pretty much you go in that graph structure and you visit every node of the graph. The ones that satisfy your constraints are marked for maintaining, and the remaining ones are marked for rejection. The ones that are maintained, that are retained, are used for producing the segmentation result. So these operators can be both interactive or automated, so we have supervised or unsupervised segmentation. And some of the very, very important properties of these operators is, for example, the first line, that is rotation, translation, and scale invariance. So if you think one of the problems that make us seek for massive image data sets to train CNNs is the fact that if you have this object here and you want to train a network to identify that, you need to provide sufficient examples of this standing like this, like that, like that, like that, and all the possible angles and rotations that it can have, such that the network itself is familiar with all possible viewing angles. And the other thing is, things appear very differently from close by or from far away, so the scale invariance is also particularly important. And one last one is the translation. So where is this object with respect to the x, y coordinates? We need to have the operators extending to 3D without any problem. We want them to be edge preserving, and we want the data structure to be data source or content agnostic. So it doesn't matter if it's MRI images or CT scans or you name it, we want the same technology to be equally applicable and transferable to all those domains. So on the right, I have the challenges that we had using convolutional neural network approaches, and pretty much can be summarized into the fact that the 3D segmentation algorithms are not particularly well in performing their tasks, and there are many reasons why this is the case. But let's say the most convincing class of algorithms for 3D medical image segmentation are the ones that approach every slice separately and produce segmentation there, and then they stack the results. But then you have all kinds of discontinuities that make surfaces appear as artificial. And you have a different class of algorithms that use pretty much one of those slices to perform segmentation, and then you use that as a seed into a region drawing algorithm, and then you produce the segmentation that way. And you've got also convolutions happening in 3D space, but then there's the problem of the anisotropy of data. So you don't have the same dimensions of the z-axis as you do have in the x-y. And of course, you know, if you kind of stop with the 2D example, you already see how expensive it can be to do segmentations there, and sometimes, you know, the hardware in itself can be particularly demanding as well. We use extensively GPUs, but this is something that we try to make our technology invariant. We want to make this a lightweight technology that can run pretty much anywhere. Then moving into the training data, annotated medical images are in general hard to find, and indeed, as several other speakers before me mentioned, you know, they have to be produced, they have to be annotated by radiologists, and this can be an expensive procedure. And when it comes into 3D annotated medical images, to the best of our knowledge, we do not know of any such data set sufficiently large in order to train any network. Then we have the other problem, which is like, you know, if you are to generalize this technology, you pretty much need a network for every condition or for every cluster of conditions. And, you know, that makes it difficult. So let's say that you solve the lung cancer. When you are to go to a liver cancer, you need to start all over again, which is actually a very frustrating process. And so we want to have one tool that extends to as many domains as possible. I want to emphasize on the bottom left circle, the automatic pixel imputation. What happens in the case of the instance segmentation algorithms is, for example, I remember when this technology was first introduced, they utilized an image to show how can an algorithm of the kind extract a cyclist. So there was a gentleman on a bicycle, and there was a contour drawn around him and the bicycle. And indeed, the segmentation looked very convincing, but actually, if somebody was to pay attention, they could see through the wheels the background. And that is a problem, because the background is not part of my segment, but very few algorithms can actually distinguish the two. And if you are to insist in making sure that this happens, that means that you need to spend so much effort and so much work in producing the right type of annotated data that the cost is just exploding. And one last thing that was also iterated here before is the interactivity. The interactivity is missing from the CNN approach. It means that you've got a black box, you put an input, you get an output. If you don't like it, you gotta live with that. There's nothing you can do about it. And this is an issue. You know, a lot of doctors feel indeed allergic to this technology on the basis that they do not necessarily trust blindly what the machine is delivering. It might be the perfect algorithm, but still they'll have doubts. And the reason that they have doubts is because they do not control the process. It's a black box. So we need to give them, we need to enable them to actually get to where they want to go, step at a time, without losing ability or speed or quality. It's just that, you know, it makes a whole different story if you enable somebody to produce the result in a controlled environment as opposed to just throw a result to them. So our technology is indeed addressing all these, and it uses as a starting point pretty much the complete absence of training data. It generates training data as it goes along, but it doesn't require that to start with. And as a teaser, I might just throw the next line. That is, these operators are currently being investigated as a replacement to the classical convolution in CNNs. This is work in progress, but what needs to be said about this is that they extend naturally to 3D, which is really powerful because 3D offers so much more information than the conventional 2D imaging. In those architectures that we're investigating, we have only one weight per neuron, which is also particularly important if you think the the number of neurons involved, and the number of regions accessed that are equivalent to the moving window in the case of convolutions are no more than approximately 10% of the image space, which is also massive if you think about the fact that in the CNN approach, you've got a sliding window that scans through the entire content of the image, and for every pixel it centers itself, it gets a neighborhood and does what it does. So this is work in progress. Hopefully next year we might be able to report something more on this. This is an example of the graph data structure that we used recently to produce some of the results that we'll see later, but I'm not going to insist too much on that because it can take us beyond the scope of this presentation. This is an example of the graph space. This is shown in fisheye view. We usually have billions, if not trillions, of endpoints, and what we're doing is pretty much investigating the logical transitions of these endpoints, and it is these points of attraction in the graph that tells us the nature of the objects that we're trying to extract. So the grapher in itself is part of what we refer to as the I4 technology. And I4 stands for Interactive Image Information Insights. It's a product under development, and this product can take training data if available, but it doesn't necessarily require these. What is essential is that you provide the images of the patient that you're trying to deal with, and it offers three different alternatives: the interactive filtering, segmentation, and visualization. And based on this, we can do a whole lot of beautiful things. So that was the grapher. The next thing is the feature space. And as I mentioned, the number of features that we extract can approximately 120 by now, but this is growing. So it's an n-dimensional attribute histogram, and every bin in this histogram corresponds to the normalized product of the node area of that specific graph node. That is the number of pixels that specific node corresponds to, times the lifetime. That is how much stretch does this node have before the next one in line shows up. And this is an energy factor, let's say. And you see here a simple 3D feature space that showcases what happens if you try to extract out of the image information content consistent patterns with respect to some shape parameter, size, and intensity. So we have 2D and 3D cross sections that are available for visualizations. Here you see one. And lastly, it's the switchboard, which is pretty much a feature space wrapper. So what it does is it enables you to do these 2D and 3D cross sections of the feature space, and that is for easy kind of interaction with the data that are being represented in the feature space. And it allows you to actually go in there and decide what entries are the ones that correspond best to the objects that you're looking for. You can do this in a fully automated manner, and I'll show some examples later, or you can actually do that manually in the absence of good algorithms to do that for you. So here is an example, and there is a cluster there. It's like a falling star pattern. And in this specific feature space, what we're seeing is at the top left corner, we have the origin, and as we move down the scale, we have features of high compactness, and as we move towards the right of the image, we have increasing in size structures. So over there, we have something that is repeating with respect to compactness and size. And this is a very simplistic example. You can have that, as I said, with 120 different such features, and you can actually draw a very nice decision surface that describes best what is it that you're looking for. In the case study that follows, this will be highlighted. So what we use as a case study is the liver tumor ablation. So this is a process where you insert the needle into the liver, and this needle is developing a very high temperature and is burning the area that has been identified as the one containing the tumor. And once this is done, there is some kind of, I believe, some biopsy done, to verify the success of the story, and some further imaging in order to make sure that it was successful. So what dictates the success of this is the ability of measuring precisely the size of the tumor, and also the ability of deciding whether it is accessible or not. So in our process, we pose the following questions. What do liver tumors look like. We can use prior knowledge for that, or we can start from scratch. Where is the tumor in the liver? So that is the part that involves the segmentation. What is the tumor size, shape, centroids, and the kind? That is going to tell us if it's operable. And the last question, is it accessible? And this is an important question because sometimes, it might be locations that require advanced pre-operation planning because, you need to take into account arteries, you need to take into account bones or other organs that might stand in the way. So, regarding the first question, what do tumors look like? A very easy way of actually populating some kind of a knowledge base for this process is just going through a couple of examples in the CT scans, whether it's 2D or 3D, and asking the specialist to draw a region of interest around it. So you see a couple of different cases of different types of liver tumors there. So this is what we refer to as data annotation. So they do draw a bounding box around the area that is believed to be the problematic one, and a label is given. And the next thing that happens is that the graph is computed for this specific image, and an automated image segmentation is generated, and the segments themselves are profiled, and this is what we refer to as the data science grade material. So this is the output of every one of these. So the part that involves the segmentation can be done in two different ways. So we have a way that pretty much mimics the magic wand in Photoshop. So you just, in Photoshop, what you might have seen is that you can actually have a tool that clicks on a specific pixel and it shows you the object to which this pixel belongs to. So in our case, we just have a rectangular selection. We draw a box around the area of interest, and then the algorithm is giving us the segment right away. And this segment is measurable. And so if you do that for the segments and for the images, you end up with the feature space that I showed you before. And in this specific example of the compactness against shape, you have the point of origin there. You've got all those tumors that have pretty much the same appearance showing up in this area here. It's a high energy area into my graph. And the everything else is lower in energy simply because you do not have the same cross-section repeating every time. So you've got different sizes of liver cross-sections, for example, or you've got the presence or absence of other features, anatomical features in there that shows up in here, thus preventing these to grow in high energy beams in this graph there. Then you've got some more high energy elements which correspond to the cross-section of the entire body. So this is like the one object, the one connected component that coincides to the entirety of the body. And pretty much, we're dealing with the same size of bodies. That's why you will have a strong response there. But we know that the two extreme are to be ignored. We're looking for structures that, at least for those two attributes out of the 120 ones, would look something like that. And as I mentioned before, you have the ability, once you're given such a cross-section, or the entirety of the feature space, you can have several advanced and smart algorithms to extract that cluster that mimics pretty much what we've seen in Ross-Gersyk's fast RCNN, mask RCNN algorithm, the region proposal module over there. But instead of actually having the image pointing to you in a specific area, in this specific example, we're having the attribute space, and we're saying that it's these attributes and it's these values that actually correspond to the objects of interest. So we get something like that because next to our core objects within our regions of interest, we have also the surrounding neighbors, which can be individual pixels. And this is noise pretty much, so we're interested in this cluster there that coincides with our pattern. So we have an algorithm that will give us this as the trace of this specific high energy area, or you can do that manually. If you have complete absence of such expertise in your lab, you can actually go over there and click. That's why it's called a switchboard, so you can click on those entries and you can do that manually yourself. And then, when there's a new case thrown in, then we have all this accumulated knowledge. So what we will do is, in the absence of interaction in this image, we will actually have all the possible objects extracted out of that because they are represented into the graph, and they will be projected into the feature space. And those that actually coincide with that area will be extracted, segmented, and you will get the magic result So throw in this, you get that as an output. In the absence of this algorithm, and given the fact that you might, start with no training data, then you can do that with a simple query. So you just specify yourself what is it that you suspect that might describe this best, and indeed, you can get the same result. And a very good question to ask once you do this is, how good is this segmentation representing my interest? So we are not doctors, we didn't speak with doctors yet. This is just purely our own empirical evaluation, but we just started this 2 months ago. So here you do see a couple of examples that showcase where we believe tumors are. We just went over there, we just encircled them, and we got these results as automatic segmentations. This is a metastatic example, which is a little bit more complicated, and we got pretty good results. And now, once you have those segments, of course, you can just measure them and decide whether this is operable, whether this is reachable, and what else do you want to do with this. So, as a tool, the switchboard, together with the buffer, it supports pretty much the every cycle of analysis. So we have the development of an initial hypothesis, and you start asking questions on your data space in order to see if that hypothesis is standing. So the exploratory questions that this EDA framework allows us to ask is, do the shape descriptors X, Y, or Z, for example, size, color, or whatever, deliver a reliable target approximation? And as a tool, it allows us to have control over the data pool, selection bias, randomization, blocking and adjustment, confounding factors, causal inference, and cross-validation. So I'm not going to go through all these. It's just a lengthy slide. So skip this one. And I just wanted to show you a couple of these 2D queries and the examples of this type of segmentations in different domains, different types of medical imaging and different types of anatomical features. This is an example of the brain aneurysms, the liver tumor we've seen before, the line segmentation, kidney stones, breast tumors, and some more impressive, perhaps, screenshots, and that is of the 3D analysis that we can do. This is the automatic detection of brain aneurysms, the stenosis. Actually, this is a very interesting result because this was actually a piece of detail that was missed by an expert. This was actually, we asked an expert to analyze this, and when you see this slice by slice, this is literally 2 pixels wide gap. So what you see there is the growth of tissue inside the blood vessel that narrows down the passage, and thus you have less and less blood delivered to the brain. So this is just a little anomaly of 2 pixels wide, and when looking at those tiny little images in the 2D case, slice after slice, you actually miss that. But it is possible that by starting with this, removing all irrelevant data, and really irrelevant data in this case means 2 things: whatever is not as elongated as the vessels, and whatever is not as big as the vessels themselves. So noise, pretty much, and compact features. That leaves you this thing behind, and then you just run a simple profiling that goes along the blood vessel and studies for width anomalies, and that's where you get this alert. Another example in the case of brain, stuck in the hippocampus, kidney stones, massive cases. And there you see actually the level of detail that this technology is delivering. So not only you actually get the kidney stones, but it also allows you to see tiny little crystal protrusions that are engaging this stone into the internal of the organ. And this is a fine detail that is very hard to actually evaluate and understand out of 2D imaging. This is the beauty of this technology and the ability of taking things to the 3D case. And this was a case of severe hip arthritis. So you see how badly this hip is going through. And the patient was having an enormous kind of discomfort. But at the same time, he was complaining about pain in the entire pelvic area. And by doing the CT scan and going in this kind of visualization, we witnessed 3 little bright dots over there that in 3D suggest that these are, it's pretty hard to say what it is from this. But it turned out that over there, it is straightforward proposition that these are tiny little renal stones that travel down the urinary tract towards the bladder. And that was the cause for the extra discomfort. There's some cranial cases that we started here, and eventually some it's interesting to see that this technology is not limited only to conventional types of medical imaging, but also all the way to confocal microscopy and get 3D segmentations of neurons like the one that you see here. And with that, let me just jump quickly into conclusions. So what we've seen is that regarding data, that training can be done one image at a time after segmentation. Training data is if they are available, they can be used in the activation of the switchboard, so we can actually utilize them directly to tell us in the feature space which are the most relevant features. And then in the case of post-processing, every such case that we run is an annotated 3D data set in itself. So it's actually added value into the institution that utilizes this technology. And this is something that we didn't manage to find ourselves. So the segmentation in itself is done on a case-by-case basis, so we can actually fine-tune the process. It's very simple and it's very straightforward, but we can fine-tune it to the exact specific condition that is of interest, and it can be done both in 2D and 3D. So the image segmenter does not require prior knowledge or training, but it can utilize that. It's not necessary. It's not limited to a specific case, but performs equally well in all challenges. And it's very fast and lightweight in memory and computation time. With respect to data science, so we've seen the automated feature extraction. Feature selection can be done manually or in using some machine learning algorithm. And lastly, and this is probably the most important slide of them all, so what we did was we actually provided a couple of manual segmentations into the system. But the artificial neural network, and I'm saying artificial because it's not a convolutional neural network, the artificial neural network that we've trained was based on blood tests, blood results, and measured segments. So we've established the relation between the two, which means that for any unknown photograph that is going to be thrown into that system, we will use the same technology as our segmentation states to propose regions, and the classification of whether this is what we're looking for or not is going to be done based on the blood results. So we're actually having instance segmentation using artificial neural networks and driven by blood tests as opposed to image features. So we use artificial neural networks, not convolutional neural networks, and we train those ANNs with numbers that are pretty much the interpretations of the segments that we've isolated before in our training stage. And this does not require any costly CNN architectures in 3D data. It bypasses the problem of finding 3D annotated data, and in itself produces 3D segmentation with a level of accuracy that we've seen before. And that summarizes my talk. Thank you very much.
Excellent. Thank you, Georgios. Now opening up for questions from our audience.
So, does the tool work standalone? Are you planning on integrating with the PACS or EHR? Like, how do the clinicians get them used?
Having just started, really, we didn't decide on the best way of delivery. So right now, we're just fine-tuning the mechanics behind it, and the way of delivering this remains to be seen. So we're pretty much listening and open to discussions on the topic. Where we are not a medical company. What we do is we develop AI products, and in this specific case, we've seen this very promising technology. We built this tool, and we want to pretty much explore as a next step, what would be the best way to make it available to the wider market. Thank you.
I'm involved in late-stage development, clinical development in oncology, and in this area, radiological progression for oncology studies is used as primary endpoints, component of primary endpoints. And question to you, and this assessment is landed on RECIST criteria. So, did you consider to relate your application for this RISC criteria, and could it be used for identification of radiological progression in oncology?
Thank you for your question. Actually, we did not consider that, but the thing is that we did not want to emphasize on one specific direction. What we prioritized is developing this technology and actually making it available to experts to try it in different areas, domains, and come back to us with feedback. So we have no idea how it will perform in this or that, but we're quite confident from what we've seen so far. That's why I had all those examples in different domains and fields of application. We're quite confident that it doesn't have really limitations. It's pretty much, it can cope with pretty much everything. But what is important for us as a next step for an evaluation of this technology is to actually indeed get to hear the opinion of experts in different domains. How well did they see it performed in their own domain.
So for 3D instance segmentation, I was wondering what is the backbone of your algorithm? Because as far as I know, the algorithm is not yet there.
The algorithm, this algorithm is there. So
what is the?
So one of the.
Is it new net or is it more?
So it is let's say an evolution of the water set, but an evolution that bypasses the problems that we've seen in the previous presentation. So it is a graph-based segmentation framework. One example, because I said the grapher can actually fine-tune the technology behind every case separately, so it can identify which graph is the best. But for most of the ones that you've seen here, the algorithm behind it is referred to as the alpha tree algorithm and alpha tree. So it is an algorithm that structures the image information content in such a way that pretty much clusters pixels together based on similarity criteria that can be as simple as intensity. So any two pixels similar to each other with intensity can be put together, all the way to super complicated.
Not a CNN?
Sorry?
Not a CNN?
No. No. We avoided the CNN for the list of reasons that we listed there. It is problematic in many different ways in this specific usage. So CNN would give us problems.
Do you have publications on it?
There are actually publications out there that they go back to 2012. So
from your company.
not the company itself, but the core algorithms behind the grapher. What allows us to do this fine segmentation is a technology that has been developed approximately 2012, as far as I remember. Yeah. These slides, I believe, are to be available, right? So there is a link in one of these slides into the relevant publication. Thank you.
One more question for you. Like if we would consider patient evolving through the time,
Yeah.
did you consider possibility to be able to analyze images were taken by different devices? Because throughout lives, patients could take devices,
Yeah.
could take imaging from different devices, and it could also be CT or MRI, but
Right.
the same area.
Yeah.
So, are you ready to deal with that kind of
We-
challenges?
We do not have a registration module in place, but I think that this is just a matter of pure engineering. But what we have is, because of the adaptability of which algorithm is going to describe the image information content, we have some technologies that work best for MRI, some others for CT. So it is possible that it is possible to deal with this case, and we're quite confident that there is no problem. It's just that the segmentation in itself might be done with a different algorithm. But no matter what, you will end up with your segmentation. So, yes. The question is, of course, registering it. If it is like a month later, for example, you need to know, and if it's with a different device, you need to know where was it before with respect to other features around you in order to position it in the right place again. And this is why I said before the pool in the pool of features that we take into consideration or we measure is the proximity to other landmarks. So, for example, we position a specific condition like a tumor in the liver, for example, not only with respect to the liver itself, but where is it with respect to bones, or where is it with respect to identifiable features that will not change from over time.
Excellent. Well, thank you so much, Georgios.
Thank
Round
you.
of applause.
Thank you.
You've seen a lot of presentations. That concludes the day one